what is the most, you know, what is the most common interval, so to speak, right? What is the most common interval of murder rates in America, and what are the relatively rare intervals for murder rates in America? Okay, so okay, I tallied all these numbers for you, um, because we obviously cannot do this, asking you to do this as we could in a face-to-face lecture. But okay, so anyway, tallying this is not very difficult. It just you need to be very careful. So here, we see that there are four states that have murder rates that's between 0 and 2.9, and you have the rest. So if I ask you, okay, so I don't know, Crystal, um, what is the most common sort of murder rates in the United States among the 50 states? Then by looking at this table, you will have no problem, or everybody should have no problem in identifying the interval, right, of murder rates that's most common in this country, and that is 3.0 to 5.9, because there are 17 states. Okay, that's the largest number compared to all the rest numbers. And I verified that these numbers are correct by summing them up, and the sum is 50. Okay, so this is also a distribution, and this tallies, the distribution, how these intervals are distributed across the 50 states. Okay. All right. So now we can sort of have a more formal definition of what we call frequency distribution. So frequency distribution essentially to list the number of occurrences, right, or the number of times that an outcome of a variable occurs. Okay, an outcome simply means a value that this variable can take, right? So in terms of our first question, the variable is the liking of iPhone. Okay, the liking of iPhone. So this variable, obviously, as we just saw, can take the value from 1 to 7. And we tally that, how many ones, how many twos, how many threes, all the way to how many sevens, right? Other than we actually observed. The second variable we look at is murder rates, right? Murder rates. Obviously, this is also a variable because this rate varies across states. And what we did is we tally, um, the number of occurrences of each interval, right? From 0 to 2.9, I believe that's the first interval, right? So how many times these intervals occurs across 50 states? Okay, so that's what we mean by a listing of the number of times that each possible outcome of a variable occurs. That is, each possible value of a variable occurs. So obviously, as you saw, the possible outcome can be concrete values or exact values, right? 1 or 2 or 7, right? Or it could be intervals of values, right? And this is most useful when the values don't repeat themselves. That is, as we saw in this case, right? Rarely, you have exactly identical numbers. That gives you too many numbers. In this case, 50. Well, if we're going to tally the murder rates across the world, when you have 200 plus countries and geographic, geopolitical regions, then you have 200 plus numbers. That simply is too many, right? Um, in that case, using intervals will be very useful. Okay. So frequency is very useful and is commonly used in many contexts. Um, and there are different types of frequencies. So what we just saw are frequency counts, right? We simply count how many times. One time, twice, three times, four times, etc. Right? we also call those absolute frequency. But what absolute frequency mean um, can vary, right? Sometimes, uh, the same frequency, the same absolute frequency can mean different things. And if we don't, you know, um, specify the context of this, absolute frequency, we might have, the wrong conclusion. So, for example, um, we can say that there, a frequency. We can say that there's a frequency of 5, right? But this frequency of 5, has very different meaning when we say we count that this outcome occurs 5 times out of 10 occurrences, or we observe 5 times occurrences out of 100 trials, 100 attempts. So obviously then 5, this number here, has different meaning. 5 in this context means, actually it means half. Half of the time we'll observe a particular outcome. But 5 in this context simply means this outcome is very rare, because 5 out of 100, that is 1/20th. That is 0.05. Am I correct? God, my math's a little rusty. 5 out of 100. Yeah, exactly. 0.05. That means 5%. That means this event in this context is, after all, not that common. It's very rare, actually. Okay, so that's what we mean, frequency, absolute frequency is useful, but it can be misleading depending on how many numbers, how many trials, or how many total occurrences that you have. Okay, so that's why we need a second type of frequency, and we call it relative frequency. And relative frequency is very close to what we mean by probability, right? So the definition of relative frequency is this: it is the proportion. Now it's not the absolute number, right? It's a proportion. It's a ratio of the observations with which the value is associated, right? And it is calculated by, right? So you have the number of observations associated with the value. So let's say the value that you're interested in is your liking of iPhone, the liking of iPhone, right? Liking of iPhone on a 7-point scale. So you're interested in, how many people scored 7. So the value that you're interested in is 7. Okay? And how many people score 7? Well, in our example, 0. Okay? So there are 0 observations associated with the value. Well, let's 0 is not interesting at all. So let's imagine that actually there are one person, right, score 7. So the number of observations associated with the value 7 is 1. But then the next thing we need to figure out in order to calculate relative frequency is, what is the total amount of observations? Okay, and we need to divide this 1, the number of observations associated with 7, by the total amount of observations. So total amount of observations simply is sample size. That is how many people we surveyed. Okay, because if the sample size, let's say the sample size is 5, that means we have 5 observations. That is, we have 5 numbers, providing that each person provides 1 number, right? So the total number of observations in most cases will be equal to sample size. Okay, so here will be, in our example, we say that there are 6 people because the number should include me, right? 5 of you plus 1, so 6. So number of observation is 5. Okay, so now we have the relative frequency. That's 1 over 5. That is 0.2. Okay, and sometimes this relative frequency is also expressed as percentages. Okay, and that's very easy to convert this fraction number to percentages. You just simply times 100, right? That gives you 20%. That means 20% of the people that we surveyed indicate extreme liking of iPhone. How about that? Okay? So now we can start to complete this table, right? So in the previous attempt, we only have the absolute frequency or the frequency counts, right? There are 4 states, 15 states that have, a moderate score, falling in this interval. 12 states have moderates falling in this interval. And the total amount of observation is 50 because we have 50 states. Each state provides a number, so we have a total of 50 occurrences or 50 observations. So then it's a very easy matter to convert these absolute frequency to relative frequency and then to percentages. We simply divide 4 by 50. That gives you 0.08. And 0.08 is easily 8%, right? Then you can do the rest, right? So 17 divided by 50, what's that? 17 divided by 50. That's 0.34. 34%. Okay? 12 divided by 50. 4 divided by 50. 1 divided by 50. Okay, so that's very easy, right? But my question is, even without doing the calculation for all these different cells, my question is, if all these numbers, right, adds up to 50 because there are 50 states, what will be the number here? What will be the total relative frequency? And what will be the total percentage? Even without doing these calculations. Okay? You want to pause to think about it. But, if you already have the answer, I can tell you right now, right? Presume that you have thought about it. The answer here should be 1, and the answer here should be 100%. That is, all the relative frequency should add up to 1 for any particular sample, and the percentage should always sum up to 100% for a particular sample. Okay? Well, you may ask why. Why is that the case? Okay? So, okay, I'll give you a very simple proof, which should make sense. Okay? So let's just use this example. Because we know, right, relative frequency equals to the sum of proportions, right? So we know the common denominator here is 50, right? Because we always divide a absolute frequency by the total number of observations. That give us 1 relative frequency. Okay, so here's 4, but I want to generalize beyond this example, so we say this is x1, right? We don't have to know what this x1 is. It can be any number as long as it's between 0 and 50, right? It could be 50, it could be 0, but it can be larger than 50 because And in a single category, the frequency count for a single category cannot exceed the total number of observations. Okay? And then we have a second relative frequency, which is x2. It can be 17, it doesn't have to be. And then a third is x3, and all the way to, I don't know how many. I can say, they're at most 50 numbers. Okay? Now, because all these numbers, all these fractions have a common denominator, we can simply write or simplify the sum into one fraction with one common denominator, that's 50, but then we have the sum up here as x1 plus x2 plus da 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 all the way to x50. Now the question is of course, what should all these numbers add up to? Well, we actually saw just a minute ago, as at least illustrated in this example, all these individual absolute frequency counts should always add up to the total amount of observations. So that means regardless what each of these values are, it can be 3, 4, I don't know, I don't care, but all these values, as in this example, they should always add up to the total amount of observations. It's 1. And the percentage for 1 is 100%. Okay, that's why. So that gives you a way of verifying your answers in the future, right? So whenever you're calculating relative frequency for a sample in the future, a simple way to verify your answer is to see whether these numbers add up to 1, whether these numbers add up to the sample size. Here is 50 because we have 50 states, and whether percentages will add up to 100. Okay, that's sort of a mathematical necessity. Okay, so previously we talked about how to use tables, right, to summarize frequency distribution or the distribution of relative frequencies or absolute frequencies. But sometimes and many times people prefer to use graphics to summarize frequency distributions. And a very common type of graphic representation of frequency distribution is what we call histogram. So histogram is typically placed at a coordinate like this. So the x-axis is the values of the variables, right? All the possible values that a particular variable can take, right? It can be, in this case, 0, 2, 4, 6. It can be 1, 2, 3, 4, 5. It doesn't matter as long as these are values that this variable can take, right? On the y-axis, we typically use the y-axis of this histogram typically plots frequencies. Well, here I use percentages, but you can use absolute frequency counts or can use relative frequencies. So if you use relative frequency here, it'll be 0.25, it'll be 0.20, you'll be 0.05, right? Doesn't matter, right? Percentages and relative frequency are the same thing. You can also plot absolute frequency count. So this is 1 occurrences. This is, I don't know, right? Depending on the total sample size. But what I'm saying is y-axis can represent all 3 types of frequencies: absolute count, relative frequency, and percentages. Okay, then we'll use a bin to represent the percentage of occurrences, in this case, of a particular value, right? So in this case, it indicates that the value of 0 occurs for about, I don't know, 12.5% by just eyeballing it. The value of 1 occurs for, I don't know, around, I would say 18% of the time, and we can go on. The value of 2 occurs for maybe 17% of the time, and we go on, okay? So in other words, the height of the bin, right? This is a bin, right? This is a bin. The height of the bin represents its corresponding frequency. So the number of this 4, so this 5. The value of 5 of this variable occurs for about 20%, right, of the time. So bin height represents frequency. And of course, what's down here can be exact values, or it can be, interval values, right? It could be that, this bin represents from 0 to 2. This bin represents from 2 to 4. This bin represents from 5 to 8, right, etc. Right? It could be intervals, right? It doesn't matter. Depends on, of course, your purpose, right? So here are some rule of thumbs, which I think can be skipped because we're not doing the actual plot here. Okay, so there are second type of graphic representation of frequency distribution, and that we call bar charts. We just saw histograms. Well, histograms is for plotting continuous variables. So recall we say that there are different types of variables, right? We have continuous variables where the values of the variable fall on a continuous continuum. Okay? So we also call those continuous data, or those data are, of interval and ratio types. But histogram is usually not used to plot nominal or ordinal data. And nominal data will be categorical variables. Ordinal variable is also categorical variables, but the category of ordinal data is ranked, right? So an example of nominal data will be male, female, right? Male, female. And ordinal data could be education level. Right, so can you say, okay, so in our data, here's percentage, how many men and how many women were included? You can say, well, in our sample, there are maybe 45% of men, whereas there are 55% of women. So this will be a bar chart, right? The 2 bars. So in a histogram, right, these guys will be called bins. But in bar charts, obviously they're called bars. Well, they're just different names, right? But for the same purpose. It indicates the percentage of a particular value that a variable would take. So men, women, they're the values that the variable gender. Gender is the variable, and gender can take 2 values at least, right? Men, women. Okay, and here the y-axis represents the percentage or frequency of the occurrences of these 2 values. Okay, so this is nominal data, right? Nominal discrete data. But at the same time, we can also plot ordinal data. Ordinal data, we said that they're just, categorical variables, but ranked, right? Education is a very typical type of, ordinal data. So we can easily tally, right? For example, how many people in our sample has a bachelor degree, how many have a master's degree, and how many have a PhD degree. So here, my example is a categorical variable, right? Family type. So this bar represents married couple with some children. This bar means married couple without children. This single mother with children, single father with children, and the rest types of families. Okay? So a very notable difference between bar charts and histograms is that the bars in a bar chart representing all these different values variable, they have a distance or space between each pair of them. And this space indicates that these values, right, they are discrete. They don't overlap, right? They don't form a continuous continuum. But if you pay attention just now, in a histogram, the bins, right, they are very closely clustered. They touch each other, so to speak, right? And there's no space between each of the two bins. That means all these bins representing the values, right? Representing values that form a continuous continuum. They are not discrete, right? And that's why there's no space between the bins, whereas there is space between the bars. So that's how we distinguish, right, categorical variable or nominal ordinal data from continuous variable or interval ratio data. Okay, so histograms are for interval ratio data or continuous variables, whereas bar charts are for nominal ordinal data or categorical variables. Okay. So now we understand distribution, right? A description of the how values are distributed across a sample, or the listing of the number of occurrences of certain value in a sample. Out of the total amount of occurrences, we can talk about sample distributions. Of course, that will be the frequency distribution of observations of a sample, and then we can talk about population distribution. That is the frequency of distribution of observations of the target population. Actually, we have already seen these sample and population distributions. So if you recall in our first assignment, when I asked you to determine whether women or men in a sample is over or underrepresented, I actually give you the information I give you are the population and sample distributions. So for example, I said, in the population, for every the ratio between men and women is 2.3 over 1.7. So that's essentially a distribution, right? We can easily plot them, right? So here is men, here's women, and this is the ratio, and this is sort of the frequency, right? So men is 2.3, women is 1.7. The bar for women is lower, and it's a bar chart because gender is categorical, right? And then I then told you, in a sample, the distribution between men and women is about, I don't know, I'm making things up, 2.0 to 1. Okay. And then I ask you, in this sample, which gender is over represented? So, the question aside, essentially I'm telling you, here is the population distribution, here is the sample distribution. Is there a match between the sample distribution and the population distribution? Right. So, easy enough. Okay? So now you see, these distributions are very useful. Okay? And of course, we said that, the sample distribution almost always will have some kind of discrepancy, will deviate, in other words, from the population distribution because you're only obtaining a subset of the people or individuals from the population. And because of this random process, there will always be some kind of differences between the sample distribution and population distribution, right? A very intuitive, property for sample distribution is that as the sample size increases, right, the sample distribution almost always will approach the population distribution. Okay, that is, will become more and more similar to the population distribution. That is, imagine, excuse me, imagine we have a population of 100,000 people here, right? And then we calculate that the gender ratio of the population distribution of gender is 2.3 over 1.7. And if we only sample, let's say, 5,000 individuals from this 100,000 individuals, then the sample ratio will be kind of similar, but will always deviate from the population distribution. But here we're saying that as we increase the sample size from 5,000 to 10,000 to 50,000, right? This ratio will become more and more similar to this ratio. Okay. And another property is the sample histogram, right? Representing the sample distribution or sample ratio will, becoming more and more like a smooth curve, right? We can easily imagine how this happens. For 100 people, imagine now we have 100 bins, right? In this histogram. So we can still see, the exact shape of these bins because there are only a limited amount of them. But as we increase the sample size to 500, from 100 to 500, you can imagine we need to split all these bins into narrower ones. Okay, and as we increase this, the number of sample sizes, we have narrower and narrower, thinner and thinner bins. And when the sample size become very, very, very huge, essentially in the end, we can ignore the boundaries of all those bins and see the distribution as a smooth curve, like this one. And of course, the shape of the curve does not have to look like this. Well, we know this is normal distribution, but it doesn't have to look like this. It can be of any shape, right? It can be a shape of very weird form. Doesn't matter as long as it's smooth. It's sort of a curve, right? That's what it means. Now, once we have the distributions represented in curves, we can start to talk about the different types of histograms or distributions in terms of the shape, right? So imagine this is a very beautiful distribution. Well, it is very beautiful distribution. That simply means, right, most of the values, right, so these are extreme values. So this, this sort of distribution says, or histogram of distribution says, sure, there will be very extreme values, extremely large values, extremely small values, but these values will have very low frequencies. That is, they don't occur very often. They exist, but they don't occur very often. In contrast, the values that are moderate, right, not extreme, they will occur more frequently because they are higher, right? Imagine we have some kind of bins under these curves, right? Under this curve, then we see, well, indeed, it has higher, larger amount of frequencies than these values, which will have lower bins. Okay, so this is what this normal distribution means. But we don't live. Okay, so now here are some nice properties about this normal distribution. It's bell-shaped. It looks like a bell. Okay, let's clear all these now. It looks like a bell. It's symmetrical. That is, if I impose a line through the center, the two halves are exactly the same, right? We can sort of flip this half over, and these two halves should match, overlap perfectly. And most of the values, as we just saw, right, fall to the midpoint. Here's the midpoint, right? Very low, very high midpoint. So most of the values will be clustered around the midpoint, and extreme values are rare. Okay, so these are the properties of this bell-shaped curve. Oops, what's going on? And we call this part of the curve a tail. Okay, this is the center, this is a tail, and this is also a tail. Okay, now it is also very common, actually, right? We saw this type of curve, and we call this type of curve a right skewed curve because we have a tail that's stretching to the right. Okay, so this is left, this is right. So we have a tail. Whenever we have a longer tail to the right, we say that this curve or this distribution is right skewed. That simply means, right, we have more extreme. You have, fewer extreme values toward this end. Actually, pretty, a larger amount of extreme values at this end. And of course, the values, right, is not at the center because this is the center, right? Most of the values will be clustered toward this end. And toward this end, there are fewer values, right? Because, obviously the area under the curve, this portion of the curve, is larger than, I'm sorry. Because obviously if this is the center, right? The area under this part is obviously larger than the area of this part. So that means there are more values clustered toward the left, to the left of the mid value, and there are fewer values clustered to the right. When do we see this distribution? We see this distribution when we have a very difficult examination. Imagine on the x-axis we have the exam scores from 0 to 100. Okay? If this examination is very difficult, that means more people will have low scores and only a few people will have the perfect score. Okay? Most of you here will be 50. Right? Fewer people will have 100. In contrast, we can have the left skewed distribution, right? That means in this case, right, most of, I'm sorry, eraser. It means that in this case, most values would occur to the right of the midpoint. So midpoint's here, right? So most of the values will occur to the right because the area under, in this part is obviously larger than the area under this part of the curve. Okay? So this will happen, as you can also imagine, when we have an easy examination. That is, lots of people will have, very high scores, but, very fewer people, right? Far fewer people will have very low scores. Okay? So there are common properties between these two skewed distributions. Of course, they're asymmetrical, right? That means if you impose a center line and you flip this portion of the distribution to this part, they will not overlap, obviously, right? So that's why they're asymmetrical. And as just said, most values will fall to one side. For the left skew distribution, most scores will fall to the right side because for left skew distribution, the tail is longer to the left side. That means more values to the right. In contrast, for the right skew distribution, the tail is longer to the right. That means there are fewer scores here, but more scores to the left of the midpoint, to the left side, in other words. Okay? All right, so this is our first class on descriptive statistics. So we talk about the definition of descriptive statistics, and we then define what distributions are, right? Frequency, absolute account, relative frequency, percentages, and then we talk about the different plots, right? Graphic plots of the distributions. Okay, so we'll continue tomorrow to look at how can we use numbers, right? So far we use graphics to represent distributions. Tomorrow we'll be looking at how we use numbers to describe data. Okay, see you tomorrow.